So hello everyone. Today we'll try to do some numericals and design of compression members. Let us take one example. Let's take one example. So what is that? Design a single angle. Strut connected to the gusset plate to carry 180 kilonewton factored load. The length of the strut between center to center connection is 3 meters. The length of the strut is given is connection center to center connection is given as a 3 meters. This is a given numericals example. So we need to design a single angle struts. As for this, we need to design a single angle struts. Now let us start designing. Let's start designing the compression members. Your first step is to we need to assume what is the design compression stress. Your first step is to assume the what is the design compressive stress, means FCD we need to assume. So what is the value of FCD? So for angle sections we can assume FCD value between 90 to 120. So we can assume FCD values between 90 to 120 Newton per millimeter square. So we can assume the what is the value of FCD. So here since my angle this section is single angle, so I assumed FCD value is 90 Newton per millimeter squares. Your next step is to we need to calculate the what is the area required. So you need to calculate what is the area required. You know that what is the FCD here. You know that from page number 34, PD equals to A into FCD. So here I need what is A. So here I can calculate PD by FCD. So PD here, so I can take PD means what is the maximum force factored load. So I can take factored load. So factored load is how much? 180 into 10 raised to 3 divided by FCD. So what I assumed is 90 Newton per millimeter square. So from this formulas I can easily calculate what is the section area required. So is there in page number 34, IS 800. They given what is the design compressive strength, that equals to A into FCD. So this is how I calculated. Here you can check here the area required, section area required. I calculated A equals to 180 into 10 raised to 3 divided by 90. So it comes to be 2000 millimeter square. So it is 20 centimeters. So from the steel table, select the from the steel table, select the suitable sections for the required area. So I selected the sections 90 by 12 mm, which has a gross area of 20.19 centimeter squares. Similar way, from the steel table, I taken the what is the value of R minimum. R minimum means radius of gyrations. So I taken what is the value of R minimum. So that is radius of gyrations. Then let us say we need to take minimum value of radius of gyrations RYY RXX. So given is minimum, we need to take. Let us say RYY is minimum, so it is 17.4 mm. Now next step is we need to calculate what is the effective length. So as I explained in the earlier classes, so how to calculate effective length is based on connections and end conditions. So here I am providing the let us say I am providing the bolted connection. So here I am providing more than one bolts. So I can assume or I can take the effective length as 0.85 into L. Please remember, so if you are taking more than one bolts, I can take what is the effective length? Effective length equals to 0.85 into L. So or if you have you can see here, so while calculating the effective length, you can see here, so for angle with a single bolt, if you have angle with a single bolt, we need to take effective length equals to L equals to L. For angle with more bolts, means more than one bolt is there, so I need to take effective length equals to 0.85 into L I need to consider. So if it is welded connections, you are providing welded connections, you can take effective length equals to 0.7 into L. So here I am selecting more than one bolt, so I am providing more than one bolts, then effective length I can take L equals to 0.85 L. So based on these conditions, I calculated what is the effective length. So So here I am providing more than one bolt. So here I am provided effective length equals to 0.85 into L. So I calculate it comes to be 2550 mm. Then calculate the what is the slenderness ratio. Slenderness ratio, how to calculate slenderness ratio? So I can take by L effective length by R minimum. Effective length by R minimum, KL by R. That's what KL is, effective length by R minimum. R means minimum radius of gyrations. R minimum, that equals to, so I calculated lambda equals to 146.55. Then your next step is to, you need to go for the, check for the buckling classes. You need to check for the what is the buckling classes. So for buckling classes, it is an angle section. So you can go table number 10. You can refer the table number 10. You can refer table number 10 for the buckling classes. For angle sections, it comes to a buckling classes is C. So we need to check. So for that buckling classes C, and for lambda and Fi values, for yield stress and lambda values, so we need to calculate what is the what is the design compressive stress. So here you can check from the table number 9C. First you need to check which one is the buckling class. The section belongs to which buckling classes. So we need to check the section belongs to what which classes. So buckling class. So here is I am using by angle section, so it belongs to the what is that it belongs to the buckling class C. Then we need to go for design compressive stresses for buckling class C. It is there in table number 9C. IS 800. So for Fi 250 and for lambda 146.55. So we need to do the interpolations, then calculate what is the design compressive stress. Okay guys, so please remember, first we need to check it belongs to which buckling class. Is that belongs to buckling class A, B, C or D. So mine is selected section is what? Angle section. So it is belongs to buckling class C. Then you need to go for table number 9C. That is belongs to the buckling class C. 9C. Then for Fi 250, for yield stress 250, and for lambda what we calculated, this is how much you calculated. We calculated it is 146.55. For that we need to check what is the design compressive stress. We need to do the interpolations and we need to find out what is the design compressive stress. So from that from table 9C I got design compressive stress FCD equals to 54.6 Newton per millimeter square. This is the value of FCD, guys. Please, this is the value of FCD. Yeah. So please remember, you need to check first buckling classes. Then we need to go for the respective table. So mine angle section is comes under table number 9C. Then for given yield stress for Fi 250 and lambda, what we calculated, for that lambda we need to calculate what is the design compressive stress from the table. So it comes to be 54.6. So for the required values I got. Then you need to calculate what is the compressive strength. What is the compressive strength means we need to calculate by using the formulas. What is that? By using the formula, what is that? PD equals to AE into FCD. We need to check this one. What is the design compressive strength? So I already calculated what is the FCD and I have already gross areas. Area of cross sections. Then calculate what is the design compressive strength. Then design compressive strength I calculated by using this equations. So it comes to be 110.239 kilonewtons. Then we need to check along with the factored load. So we can clearly see here what we got, the design compressive strength means PD. It is PD, guys. Please, it is PD. So it is PD. So what do you calculate design compressive strength? PD, it is lesser than the factored load. So we need to revise the sections. Please remember. So we need to revise the sections. So because what is the design compressive strength is lesser than the factored load. That's how we need to do. Now let us check. So as per that, I need to revise the sections. So I need to revise the section. So now let us try. Then once again go to the steel table. Let us once again go to the steel table. So I selected the another cross section. Let us take 130 by 130 by 8 mm. It has a gross area of how much? Cross section area of 2020 millimeter squares. Then there I selected what is the R minimum, means minimum of radius of gyrations. Then I calculated what is the lambda. Lambda means what is that? Slenderness ratios. You already calculated what is the effective length divided by R minimum. You do it, you will get the what is the lambda values. Then so for lambda equals to 100, and for what is that? Yield stress equals to 250 Newton per millimeter square. Once again you need to go for the table number 9C for buckling class C. So it is angle section, so it is belongs to it belongs to buckling class C. Then so you can go and check, guys, please, the respective cross sections. You can go and check table number 10. There they given the section belongs to which buckling class. So my what I selected cross sections, it is belongs to buckling class C. Then you need to go for the table number 9C. Then for lambda equals to 100 and Fi equals to 250, we need to take or calculate what is the FCD from table number 9C. Then so here this is PD. So this is PD, guys, please. This is a design compression strength. Design compression strength equals to area into, this is the area into FCD. We need to do it area into FCD. So area into FCD. PD means design compression strength. This area into FCD. So it comes to be 216.354 kilonewton. So it is greater than the factor load, hence it is safe. So like this, guys, please, you need to do it. You need to revise the sections and you need to find out the what is the design compression strength. Okay, guys, you need to check for the design compression strength. Please remember, so as soon as you find out the what is the selected design cross sections, you need to check for the design compression strength. Means whatever the design compression strength is there, it should be greater than the factored load. So you need to check like this. Then next, as usual, your next step is to go for the connections. That is, I am providing the bolted connections here. So let us so it is given in the problem. So for M20 bolt and property class 5.6, so this is given in the problem. So there M20 and property class 5.6, you need to calculate bolt values. So first in shear, so we need to calculate what is the VDSB. In shears means what is strength of the bolt in shears, we need to calculate. Then we need to calculate strength of the bolt in bearing. We need to calculate what is the strength of the bolt in bearing. So which one is the minimum between these two values, we need to that will be considered as a bolt values. Okay, guys, now let us calculate what is the VDSB. So VDSB, so what is that? M20 bolt for property class 5.6. so diameter of the hole will be taken as 22 mm, means 20 plus 2 mm, so it's a 22 mm. So let us calculate VDSB equals to what? 1 by gamma MB into FUB by square root 3 NN into ANB plus NS into ASB. Here I will take NN equals to 1 and NS equals to 1, means shear plane in threaded portions. In shank there is no shear plane, so I can take NS equals to 0 and NN equals to 1. Based on this, I can calculate what is the VDSB. Similarly, let us calculate what is the in bearing. You need to check for the strength of the bolt in bearing. So let us calculate what is the edge distances or end distances. E equals to 1.7 into D naught. So let's take this a 40 mm. Similarly, I calculate what is the pitch distances. What is that? 2.5 into D. Now let us calculate what is the KB values. The KB value should be minimum of these four conditions. What is that? KB equals to E by 3D naught. It should be then it should be minimum of P by 3D naught minus 0.25 and FUB by FU and 1. So I calculated as per the E and P values, I calculated KB values. So you can see by using this, I can say using these four values, I can say KB taken as 0.507 mm. Okay, not mm, sorry, KB is taken as KB is taken as 0.507. Now then so now we can see, like let us calculate what is the VDPB. So based on the KB value calculated, let us calculate what is the VDPB. So calculate what is the VDPB. VDPB equals to what? So VDPB equals to 1 by gamma MB into 2.5 into KB into T into D into FU. So here I calculated what is the VDPB. Here KB is minimum of are those 4 values. So it is I taken as what? 0.507 into 8, 20 into 410. 410 is the ultimate strength of the plate. Guys, please remember you need to take FU as what? Ultimate strength of the plate you need to take. Don't take it as ultimate strength of the bolt. Please remember here. So I got the VDPB value as 66.518. Then bolt value should be minimum of those two, VDPB and VDSB. Then bolt value equals to 56.59. So it is minimum of VDPB and VDSB. Then calculate what is the number of the bolts required. So force divided by the bolt values, I got number of the bolt as 4 numbers. So this I diagrammatically represented here, schematically represented here. So these are the connections I given. So this is the number of the bolts. So what we provided, 4 numbers, all those things I give here. Okay guys, so this is how we need to do. This is how we need to design the compression members. This is how we need to